In this video, we will talk about average rate of change and secant lines, and then instantaneous rate of change and tangent lines. So average rate of change, if you recall from pre-calculus, is just a change over some time interval. Okay, it's your slope formula. So this could be delta y over delta x. It could be y2 minus y1 over x2 minus x1. The takeaway is it is the slope. Okay, so find the average rate of change over the interval from 1 to 3. So I'm going to do f of 3 minus f of 1 over 3 minus 1. So plug in the 3, you get 27 minus 3, which is 24, minus 0 over 2, which is 12. So that is the average rate of change. In this video, we're going to talk about tangent lines and instantaneous rate of change. So instantaneous rate of change is a change at one particular moment in time. So if we talked about, let's just talk about speed or velocity. I'll use them loosely. Okay, they're a little slightly different, but we could just say speed. So let's say you're traveling for 2 hours, and your average speed over the duration of the 2 hours is 50 miles per hour. That means maybe at one point you were driving 30 miles per hour, maybe another point you were driving 65 miles per hour, but the average speed is 50 miles per hour. Instantaneous rate of change says, well, what speed was I driving at, let's say, 1.5 hours? That's what instantaneous rate of change. And calculus allows us to do that, and the tangent line. So a tangent line is a line that touches a graph or a function at one point. A secant line runs through like that. Okay, so this is your tangent line, is the red one. So it's your tangent line, that is your secant line. So we're going to focus on the tangent line. Now, for me to try to find the slope at this point would be impossible to do because it's only one point. So the x value and the y value, when you subtracted it, you would have the same values, right? So you get 0 over 0. So we can't use traditional math for this. We can't use traditional slope formula for this because we're going to end up with something like 0 over 0. All right, so here we go. So let's kind of take a dive into it. So let's say I wanted to find the slope of the curve at that point. What I could do is I could find the slope of the tangent line at that point, and that would represent the slope of the curve at that point. So if I do a tangent line here, so let's say here. Okay, so if I could find the slope of this tangent line, so the slope of the tangent line, it is what it is, the entire duration of the line. So the slope of this tangent line is the same the entire time. So when it gets to this point, it's going to be the same value. So if this was 3, let's say the slope of this line was 3, then the slope of the curve at this particular point is also equal to 3. But how are we going to do that? Well, I could use the secant line to approximate it. That would be one way to do that. So I could say, well, I could just pick 2. I stay here with this point. I throw a random point up here, draw the secant line, find the slope, and say, well, it approximates my tangent line. Well, this doesn't do a great job approximating. The good news is they're both positive and positive, but not a great approximation. Well, what if I kept this as a fixed point and I brought this down? So I'm going to bring this down to here. Let's say I'll cut it in half. Well, now if I drew a secant line through that, it's kind of tough to be accurate on this, but if I drew a secant line through that, and I said, well, how does that do? How does this light blue line approximate my green line? And one would say it does a better job. It's getting better, right? If I brought it in even a little bit closer, let's say I brought it to here, and I drew a secant line. Like that. And I could say, well, how does the black line represent my tangent line? And it's getting better, right? We would agree that as the point gets in closer to my fixed point, the secant line is becoming a better representation of my tangent line. So let's look at what's happening here. We're going to call this point, I'm going to change it up a little bit. I don't like all the letters that they're using. I'm going to say, call this X. So then this point P would be x and then f of x, right? That's just normal function notation. I'm going to call this, instead of calling this h, I'm going to call this delta x. So I'm starting at this point and I'm going out some amount. That's my change in x. So this is going to be x plus delta x. Therefore, this point would be it would be x plus delta x, comma, f of x plus delta x. All right, hopefully you're with me so far, but all this is function notation and just points. Okay, again, I have my point x, and this would be f of x. I'm coming out some amount to get to this, so x plus delta x, and then the height is f of x plus delta x. If I just did the slope between these 2 points, it would be f of x plus delta x. Remember, y2 minus y1 minus f of x all over delta x. My change in x, right? This is a sophisticated slope formula. Okay, so now let's talk about what was happening here. Would you agree that as each point got closer to this fixed point, that my delta x kept getting smaller? Like first I was here, then I was here. If I did it again, I would have been here, then here, and then here. And I just keep bringing this in closer and closer and closer. My delta x is getting so tiny that delta x is getting so small that it's going to 0. Okay, and that's where limits come into play. If I said the limit as delta x goes to 0, so the space in between here and here is going to 0. This point here is really going to become this point. Okay, so the limit is delta x goes to 0, f of x plus delta x minus f of x all over delta x. This now is the formula for the slope of a curve at a point, aka it's called the derivative. Okay, so what calculus allows us to do is to find the slope of a curve at a point, and that's what we call the derivative. Now, I often call this the fun formula. This is the long way to find derivatives, okay? I'm going to give you a quick little lesson here. If you had something like this, y equals x squared, we're going to do this in 2.2, and we're going to do the power rule, and it's a shortcut to finding derivatives. Notation is y prime for the derivative. All you're going to do is take the power, you multiply it by the coefficient, you rewrite it, and you lower the power by 1. So 2x is the derivative of that. This is the slope of that graph. So let me make the graph here real quick. And you say, well, why does it have a 2x in it? Well, we know that this is a parabola. And if I ask you for the slope, it depends where you are in the curve, right? So if you're over here, and I drew a tangent line, remember the tangent line? The slope of the tangent line represents the slope at that point. You have to understand that. The slope of this tangent line is the same slope the entire duration of this tangent line, so it's the same at this point. Would we say this is a positive slope? It's kind of steep, right? But if I came over here and drew a tangent line, now it's negative. And if I came over here and drew a tangent line, now it's 0. That's why the slope is represented with an x in it. It changes. Because that's the whole point of calculus. It's constantly changing. Okay, so if I plug in a positive x value, so if I'm over here on my graph where x is positive, this will come out positive. That's why all my tangent lines shown here are positive. If I put in a negative value, it's always going to come out negative. It's going to put me over here. All my tangent lines are negative. Now they're less negative, right? Maybe here it's like that. All right, so let's kind of work through this. We're going to do the fun formula, very limited amounts of time. So I'll probably just have you do it once or twice, and then we're going to use the shortcuts, obviously. Okay, so let's do the shortcut just to check ourselves. So f of x is x squared. So the derivative, I'll call it f prime of x. You're going to bring this down, lower the power by 1. So hopefully when we're done, we get 2x. Now remember function notation. Because with function notation, if f of x is, let's say, x squared, and I wanted you to do f of x plus 1, remember you take the x plus 1, you plug it in for the x, and then you do whatever the function is asking you to do. So the formula is going to be the limit as delta x goes to 0. It's f of x plus delta x minus f of x all over delta x. So I'm going to plug in x plus delta x into the x. So I've got the limit as delta x goes to 0. So it's x plus delta x squared minus x squared over delta x. Right now, if you plugged in 0, you get 0 over 0. So if we remember from limits, whenever you get 0, 0, we should be able to simplify it. So I'm just going to FOIL it. I've got the limit. As delta x goes to 0, you get x squared plus 2x delta x plus delta x squared minus x squared over delta x. So this cancels. Again, if I plug in right now, we're going to get 0, 0. I'm going to factor out a delta x. So you get 2x plus delta x over delta x. Cancel, cancel. Plug in 0. This goes to 0. I get 2x. And that's what we got by using the shortcut. So that's this. You could think of it like this. I like to think of it as this is sort of a general formula for the slope for this particular curve, for the x squared curve. Okay, it's ever changing. It depends where you are on the x-axis. Because again, if this is a parabola, right, x squared is a parabola. If I'm over here, my slope is positive. If I'm over here, my slope is negative. All right, find the slope of the curve. One more time. After this, no more fun formula. Shortcut, f prime of x is 2x plus 2. So hopefully when we're done, we get 2x plus 2. So the limit as delta x goes to 0. So it's f of x plus delta x minus f of x all over delta x. So limit as x goes to 0. So I'm going to plug in this. So it's x plus delta x squared plus 2x plus delta x minus f of x. So minus x squared minus 2x all over delta x. So limit as delta x goes to 0. So x squared plus 2x delta x plus delta x squared plus 2x to delta x minus x squared minus 2. Let's simplify this. I'll bring back in the denominator in a second. This cancels, that cancels, this cancels, that cancels. I can take out a delta x. You get delta x, and then you get 2x plus delta x plus 2 over delta x. Cancel, cancel. This goes to 0. We get 2x plus 2, which is what we got when we did the shortcut. Now they're asking us, what is the slope at x equals 2? Remember, this is a general formula for the slope of that curve. So it's changing. It changes, okay? So now we want it when x equals 2. So I'm just going to do 2 times 2 plus 2, which is 6. So at the point x equals 2, the slope of my curve is a positive 6. A normal line is just another name for a perpendicular line. If you remember from, I guess, algebra, if we had perpendicular lines, so perpendicular lines, remember the slopes are negative reciprocals, okay? So normal line is just a perpendicular line. So find the equation of a tangent line and normal line. So going forward, we're not going to use the long formula, okay? Now, you could look at this. It's y equals mx plus b. We know the slope of this line is 3. Well, let's do the shortcut, the power rule. So if f of x is 3x minus 4, and we'll do this in 2.2. It's very easy to do. You feel very comfortable with it. But f prime, the derivative, remember you multiply, you lower the power by 1, so x goes to 0. So we just get 3. So the slope of my curve is 3. Now this is a line. Let's see if you can make the connection here, but this is just the line -4. It looks like that. So it's the same, it's a constant slope, right? We know that a line has a constant slope. It's the same slope for the duration of the line. This is your m, and we just did the derivative to also get the slope. So they want it at x equals 1. So we're going to say y minus y1 equals m, and then x minus x1. So y minus y1 equals 3x minus 1. The only thing we're missing is the y1. They didn't give us a point. They only gave us an x value. Remember, to get the y value, we would just plug it in. So we're going to get 3 minus 4, so it's -1. It's the point 1 comma -1. So it's y plus 1 equals 3x minus 1. You can just leave it like that. Now for number 6 and number 7, average rate of change is normal slope. Average rate of change is just y2 minus y1 over x2 minus x1. Instantaneous rate of change is the derivative. This is the derivative. So this is going to be f of 2 minus f of -1 over 2 minus a minus 1. I'd have to do f of 2. So f of 2 would be 4 minus 8. I get -4. I'd have to do f of -1. So I would get 1 plus 4, which is 5. So it's -4 minus 5 over 3. -9 over 3, which is -2. So number 7 is asking for the instantaneous rate of change. That is the derivative. So we're going to do the shortcut. So I'm going to say f so if f of x equals x squared minus 4x, then f prime of x, we're going to do the power rule, which we're going to do in 2.2, but it's 2x minus 4 instantaneous rate of change. It would never be over an interval. This was a typo. It would be at, let's say, x equals 3, for example. So we would do f prime of 3, so 2 times 3 minus 4, 6 minus 4, which is 2. So just make that correction. That was a typo. It would never be over an interval. It would be at a particular moment in time. So in this case, I said let's do it at x equals 3. This last slide talks about when is a function differentiable or not differentiable, I guess. So it says if a graph is well behaved, unbroken curve with no sharp turns, vertical tangents at a point, then the derivative exists. So what has to happen for a curve to have a derivative at a point, the slope from the left has to equal the slope from the right. So for example, if I have a curve here, I can draw a tangent line. If I could draw the tangent line, the slope of this curve, whatever it is, let's say it's 5. The slope is 5. That's a long line. That means the slope is 5 here and there, and 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 there, and there. So the slope has to be the same from the left and from the right. that makes it differentiable. If you look at this as sharp point, as I come in this way and as I come in this way, the slope of this line is negative. So this is -1. The slope of this line is positive, so the slope from the left does not equal the slope from the right. That is why a sharp point, sometimes we see it as a cusp. The slope is not the same. The second case, where this derivative does not exist, is a vertical tangent line. It's hard to see here, but there's a vertical tangent line right there. And then the third case would be when it's not continuous. Okay, so here the graph is either continuous or not continuous. Obviously, you can write the derivative at a point. One thing you need to note, that if something is differentiable, it has to be continuous. So if it's differentiable, it implies continuity. If it's continuous, it doesn't mean it's differentiable. Think about this graph right here. This is a continuous graph. It's not differentiable. This is a continuous graph, not differentiable. This graph is differentiable, therefore it's continuous. So it's a really important thing to make note of. So differentiable implies continuity. Continuity does not necessarily imply differential.